Good morning to all the attendees and welcome to this week's live webinar. My name is Johan van Niekerk and I'll be your host for today's session. We are joining our Durban sales manager, Rylan Sikdale, who will be covering the topic Increase Machine Availability by Adopting Real-Time Maintenance. As normal, just a few house rules that we need to go through. It's important to note that the webinar is being recorded. Please make use of the Q&A area to post any questions or make any comments. It's also very important to understand that the post will be posted anonymously to myself and no one will be able to see any questions or comments made. On our website, you can access all previous webinar webcast recordings, Q&A documents, and presentations in a PDF format. So without any further ado, let's join Rylance to learn more on how you can increase machine availability by adopting real-time maintenance. Thank you very much, Rylance.
Thank you, Johan, and a very good morning to all the attendees. And I would like to first start off by officially introducing myself. My name is Rylan Sikdale, and I am the sales manager for the KZN region located in Westville, Durban. So today our topic is real-time maintenance. So this is a rather large topic and consists of various technologies and solutions that was previously covered in other webinars. So let's have a look at our agenda for today. So we're firstly going to start off by looking at what real-time maintenance actually is and why it is important, followed by what information and where does real-time information come from. All right, then we're going to look at the data transfer, and that is what carries this information and why is this technology needed for real-time maintenance. And then we're going to be looking at how we're going to manage this data, how we're going to actually collect, sort, and visualize this real-time maintenance data. So what is maintenance? All right. So maintenance is the function whose objective is to ensure the availability of a piece of equipment. So it can be measured, also it can be time-based, where predictive and preventative measures or maintenance can be triggered by time intervals, or it can be condition-based, where the condition of the equipment will dictate when and on what maintenance needs to be performed. So at this point, it's very evident that maintenance is required on every piece of critical equipment to ensure the availability of our process of production. So it can also be safe to say that performing maintenance ensures an increased overall equipment effectiveness. All right, so what is OEE, or overall equipment effectiveness? So OEE is a mathematical calculation, right, which determines on how well your production or your piece of equipment is performing. And it's calculated by looking at three different aspects. The first aspect is availability. So availability is basically the percentage of machine runtime during a planned working day. And this is calculated by obviously subtracting the time taken for unplanned stoppages or breakdowns and setup and changeovers. The next aspect is performance. So performance is calculated by showing the difference between the actual speed as compared to the designed maximum speed of your machine. So this as well takes into account startup and warm up as well as idling speeds. The last aspect is quality. So quality is actually a comparison of passed or failed products and is indicated as a percentage. So the overall equipment effectiveness of your machine is actually calculated by multiplying these three variables together, and you get an OEE calculation in the form of percentage. So what is the focus area when you're looking at OEE when it comes to real-time maintenance? It actually affects availability the most. All right. So how can we increase the availability of our machine? And that's our topic for today. So there are various maintenance strategies that can be adopted to increase our availability on our machines. And there are three main strategies that I would like to discuss today. And each of them have their associated costs that go with it. So the first type of maintenance is reactive maintenance. So reactive maintenance is basically a run to failure strategy and it has the highest cost of ownership because of the unplanned downtime and secondary damage to equipment. So although this may seem to be the worst type of strategy that one can adopt, it does have its place. I mean, a run to failure strategy can be implemented on equipment that is not critical to your process and that is probably very cost effective to replace. The next type of strategy is a preventative maintenance strategy. So this is where downtime is planned before failure. All right, and it's associated with very high maintenance costs because parts and labor are normally consumed prematurely. So over maintaining something sometimes can actually shorten the lifespan of the equipment, and it's also prone to incorrect fitment. The last type of strategy is a predictive maintenance strategy. So this is related to condition-based monitoring or maintenance. So data is gathered in real time and maintenance is performed only when required without affecting your production. So this is the preferred overall maintenance strategy that comes with the lowest downtime and associated costs thereof. And this is the area that we're going to be focusing today. So how do we actually implement a real-time monitoring or real-time maintenance strategy? So we're going to be looking at three aspects of it. So firstly, we need to capture the data. So we need to capture operational data. So this data must be continuous and provide information about the processes that relate to the condition of our machine in real time. So what type of data can we gather? We can look at things like vibration, we can look at temperature, pressure, oil quality, and a whole host of other relevant data that can help us. The next area that we're going to look at is actually assigning and analyzing this data. So now that we have the data, it's useless until it's actually analyzed and becomes meaningful. And we can use this data to monitor counters. We can use it to monitor the runtime of rotating equipment. We can even set warning and trip limits to indicate an imminent failure. We can also monitor drift within sensors. So the last part is to actually make an informed decision. So now that we have analyzed the data, we need to act upon it. So this can be done in many ways. We can either create dashboards and create notifications on them. We can automatically send email and text messages and trigger MES systems. So according to a worldwide survey, 85% of machine downtime is caused by wear. So let's begin by looking at what data we can gather for real-time maintenance to detect this wear. And the first type of data that we can collect is vibration. So vibration, every machine vibrates from the time it's installed right until the time it breaks, right? And vibration is actually the earliest indicator of a problem. So looking at the illustration on your screen, you find that long before the breakdown actually occurs, long before temperature sensors can pick up the heat generated by friction, and long before a noise can be heard, there are unusual vibrations that occur. And it's at this point that we would like to measure these vibrations so that we can make a decision. So what are the other benefits of measuring vibration? So we can interpret the machine health before the machine breaks down. We can implement key condition indicators to establish baseline readings for equipment. So we can perform machine learning using information that's gathered by monitoring vibration. And we can use various frequencies to perform an in-depth root cause analysis during a breakdown. So what is the solution? All right. IFM has a solution to monitor vibration from a simple fan application or simple machines all the way up to complex machines, including gearboxes and compressors for that instance. So the IFM Octava system can be used to analyze complex waveforms to actually pinpoint the point of failure on a piece of equipment. And the main features of the system is that it can monitor key indicators to predict and plan maintenance. You can also have seamless integration to whatever PLC you are using via Ethernet protocols. And it also has a line recorder agent embedded for communication, so we can create interfaces between servers that are databases or speak to a SCADA system or an historian, for instance, and like a smart observer software as well. So what other information besides vibration can we use for real-time maintenance? What about oil quality, right? So oil systems are common in all industrial machines, and maintaining a contaminant-free oil supply is necessary for trouble-free operation. So oil quality sensors monitor the oil degradation and moisture ingress in real time. So you also find that premature time-based oil changes are expensive and can be replaced by condition-based oil changes, improving our machine performance and reducing our operating costs. It can also be used for early detection of mechanical issues. So real-time insight of developing mechanical issues can be quickly identified and corrected before primary or secondary damage occurs. So now that we know that we can use oil quality information for real-time maintenance, what sensors provide this information? All right, so monitoring the moisture content in a oil, a hydraulic or lubricating oil is critical to prevent mechanical damage of rotating equipment. And we can find that excessive moisture can rapidly degrade bearing surfaces, leading to failure and secondary damage. So the LDH100 sensor from IFM actually measures the water content in the oil and transmits this data as a percentage to indicate relative humidity as well as the temperature output on it integrated. So what other information can we get or using or monitoring our oil quality? A particle counter. So particle monitoring is a very effective real-time monitoring method to protect oil systems and to detect mechanical wear. And a common application where this is used is for lubrication of gearboxes. So as soon as a gear mesh frequency is detected and amplitude starts to rise, you would normally see an increase in the particle size as well as the particle count in the oil. And this is an indication of wearing of meshing gears. Another form of real-time data can be achieved from valve feedback. So now we can do condition monitoring on pipelines. So IFM's MVQ valve feedback system or sensor for corrosion actuators have the benefit of monitoring due to the following features. So the position feedback in terms of degrees. So not only can you now indicate whether the valve is open or closed, you can also get that position of exact degrees. And with this information, you can tell if something is jamming within the valve body, or you can indicate if there's scaling on your pipeline. Another feature is we can monitor the time it takes from the valve to actually open and close and vice versa. And this could be used to indicate whether our actuator is passing or not. The next feature is that we have seat monitoring. So now it's possible to not only see if your valve is seated, but also to detect if your seat is actually wearing. We also have a visual indication on the sensor itself to tell you whether the valve is open or closed, but it also has a bright red LED that will blink to indicate if there's a fault on a valve. So now that it also can be seen that valve feedback has the features that gives us a benefit of providing real-time maintenance data that can be used for condition monitoring. The next type of data is compressed airflow, okay? And in order to prevent a leak, we first need to detect it, right? So by continuous monitoring of compressed air usage, areas of leakage can be quickly identified. Maintenance is scheduled to minimize downtime, and very often capital investment of a new compressor or repairs of a compressor can actually be postponed or not even required. So IFM's SD range of compressed air and industrial gases have the following features. We can measure now flow, pressure, temperature, and the totalizer using just one unit. all right? And we can simultaneously transmit this data. We can prevent downtime, obviously, by detecting leaks, and we can monitor the effectiveness of our compressor. So if detecting a leak prevents downtime due to equipment failure, then it's vital information for real-time maintenance. The next type of data that we can get is from simple position sensors. So let's look at how a conventional inductive proxy can now become a condition monitoring tool. All right. The output represents the actual distance in millimeters. Right. If we can get that data, we can identify if the target or the sensor has moved out of place. Minute changes can be detected to indicate mechanical wear of a part. Right. Freely selectable working range for the detection of can also be used to detect if a part is in place. Another type of sensor is normal photoelectric sensors. So conventional photoelectric sensors have the ability to become condition monitoring devices. For example, the OGD range of photoelectric sensors from IFM gives you an output in actual distance, right, as well as the reflectivity. So if we have this data, we can actually detect when our lens is dirty or becomes soiled. We can also detect the color change in the object that we're looking at. We can provide an indication with that information if the sensor gets misaligned. So now it can be seen how a normal photoelectric sensor can be actually used as a real-time maintenance device as well. Temperature sensors. So the TCC calibration check temperature sensor, for example, has improved performance thanks to the following aspects. So maximum reliability. So this sensor, if the sensor deviates from a defined tolerance value, or in the event of a sensor malfunction, it provides a corresponding signal by a clearly visible LED on the device, as well as a dedicated diagnostic output that can be monitored by a PLC. It has permanent status checking. So thanks to the calibration check technology, the TCC permanently monitors and checks its own drift behavior. So the sensor compares the temperature value to the simultaneously measured reference value. So it actually comprises of two elements in one unit. And if the deviation is outside the tolerable range or tolerance range, the TCC then provides a visible indication using the LEDs on the unit itself, as well as it can send a message to the PLC via a diagnostic output. Then it has transparent sensor communication. So visual and digital indication. So the TCC provides the current status in a very simple way. So if the LED is green, it indicates that the unit is operating reliably. If it turns blue, it shows you that the temperature deviation inside the unit is outside the tolerance range. And it has a red indicator to indicate a serious malfunction or a failure, such as the element inside the unit itself. So besides that, the TCC automatically stores all the data that's required for documentation. For example, the installation date, the actual operating hours, as well as logbooks or event messages on the calibration check status. So now that we've discovered that normal sensors and instrumentation can provide valuable real-time data, how do we actually get this data? Right? So what is the carrier of this data? Okay, so we're going to be looking at IO-Link. Now, unlike traditional control signals, IO-Link offers increased bandwidth and full access to the sensor's intelligence without changing the sensor and the wiring. So it opens new possibilities to maximize the overall efficiency of your machine and processes. So in general, IO-Link offers three types of data that vary from sensor to sensor. And they are, number one, cyclic data. So this is your actual process variables, right? Input and output data is continuously transferred bidirectionally for process control. With that data, we also get diagnostic information that is sent simultaneously. Then we have acyclic data. So this is data that's only required on demand. And this can include things like the sensor parameters and identification of the sensor, like the vendor number or serial number of the sensor, and specific data sets like counters. iLink can also send events data. So additional specific diagnostic data from the sensor can include things like when the sensor goes out of range or there's an incorrect parameter value that has been set. So how does iLink fit into increasing our availability? So iLink offers some unique features that gives us a benefit of applying real-time maintenance on our measuring devices, all right? And the first item we're going to look at is that there's no external influence on the signal. So the data transfer is digital and is based on a 24-volt signal. Therefore, screen cables and groundings or grounding rather is not necessary anymore. There are no measured value losses. So due to the entire value being transferred as digital, there's no need for unnecessary conversions from digital to analog and back again. So this is the pure microprocessor signal from the sensor all the way to the PLC. Then we have easy sensor replacement. So all parameters are stored on the iLink master and is automatically transferred when the unit is changed out. This obviously saves time during a breakdown. It's tamper-free. Inputting the incorrect settings are now impossible. Another feature is identification. So only like-for-like sensors can be replaced. So now you cannot make the mistake of putting an incorrect sensor for that desired application. Then we have wire break detection and diagnostics. So now predictive data and like short circuits can be immediately detected. Another nice feature is remote parameterization. So due to the software being web-based, it allows for remote login, but right down to the sensor level. So parameters can be changed on the sensor itself remotely. Scalable technology. So just like analog values, iLink 2 can be scaled according to your preference. The next feature is multiple sensor values. So iLink allows from a single sensor for you to detect multiple values. For example, we discussed the airflow meter where you can measure the flow rate, the temperature, the pressure, and the totalizer value, measuring and transmitting simultaneously from one sensor on one cable. So all of these features and benefits gives us the benefit of reduced costs. So because the signal is digital, there's no need for expensive analog cards. Normal switches, for instance, can be used instead of using expensive 4 to 20 milliamp transmitters. So in order for process control, we only need the measured variable from the sensor, okay? And that is only 5% of what the sensor is actually capable of doing. So traditionally, 95% of that data is lost or maybe remains locked into the sensor, okay? But we've just discovered now that that data is very important because we can use that data for real-time maintenance by monitoring the condition of our machine, energy monitoring, quality monitoring, and remote services. So this data is very important for us. However, it is not practical to transmit all of this data to our PLC. You're just going to slow our network down, and it's not practical for control purposes. So what is the solution to that problem? All right. The solution to that problem is to create a Y path. So creating a Y path allows for the data to be transmitted in two separate paths that are totally isolated from one another. And they're physically separated by the ports having individual IP addresses. All right. So on the picture on your screen, you can see that an iLink master, for instance, you can also have vibration as well, has one port that is dedicated for communication to the PLC via various PLC protocols, depending on what you're using. And the other port with a second IP address can communicate to a server, for instance, right? But how do we manage this data? Okay. How do we actually visualize important information in order for us to make a decision? And how do we indicate problems that require maintenance? So the next part we're going to look at is actually organizing and visualizing this data. Now that we have established that the data require, we establish what data we require, what sensors we can use, how to carry the data, we need to now interpret the data, visualize it, and make an informed decision. IFM's Smart Observer software allows you to navigate. So you can import Google Maps or a plant layout can be imported to a dashboard for easy navigation to either different sites or to different parts of your plant. You can then visualize the data. So cockpits can be freely created to make a customized dashboard showing all relevant data. So this can be represented in various ways. You can either use graphs, you can represent the value, the exact value itself, or you can use gauges, depending on what your preference is. Then you can actually analyze the data in detail by looking at the actual trends. So this allows you to do root cause analysis by comparing two different variables in one view. When something goes into an alarm condition, you can then notify the relevant personnel, right? Because the software allows you to then generate an email or a text message that can be sent to the correct person. Reports can also be generated from the software into an Excel format. So you can generate a report for reporting purposes, and you can also create maintenance tickets. So maintenance tickets can be directed to the correct person as well, so that actionable data can be taken place, or actions can be taken place rather. So Smart Observer has some core functions, right? So from the actual data source, which is our sensors, right to the point where your operator or the person that needs to see the information has to make a decision to actually take some actions. Smart Observer then collects the data, all right? Manages the data by checking the connections and notification of alarms, and also visualizing the data. So we just showed you on previous slide how we can create navigation points, we can create trends, and we can actually analyze the data, and we can also notify using different tasks. And that, gentlemen, brings me to the end of my presentation, and I hope that you have enjoyed it. But now I would like to leave the floor open for some questions. And Johan, if you can just direct us into some questions that we can have a look at.
Thank you very much, Rylance, for a very informative presentation. And I would also like to thank the audience for making some comments and posting questions. I'm going to ask a few frequently asked questions. I'm also going to monitor the Q&A section. So if there's more questions, please add them to the Q&A section and I'll post it directly to Rylance. But the first one that we have is, you talked about iLink sensors and iLink masters. Is the iLink sensor able to send information when there's any malfunction signals?
Absolutely. Okay, so as discussed, the data that's being transmitted to the PLC is consistent of diagnostic data. So we can have a diagnostic bit with a specific error code that can be sent to the PLC so that that information can definitely be read. So this will be indicative of a malfunction within a sensor.
Thank you, Rylance. The second question that we have is, how do I configure the iLink master?
All right, so the iLink master can be configured using the LR device software, and using this software you can create or set up your IP address for your PLC communication, but you can also individually set up each port. So each port mode can either be set as the IO-Link port or a digital input to output, and you can disable the port if it's not in use.
Great, thanks, Rylance. So how do iLink sensors transmit measured values?
Okay, so it's different as compared to traditional 4 to 20 milliamp transmitters, where the data or where the sensor senses the variable and then converts it to analog, and then it's transmitted over analog. So with IO-Link sensors and when using the IO-Link protocol, the data is then transmitted from the microprocessor all the way to the IO-Link master in the same format. So it doesn't change, neither is it converted while it's being transmitted. And at the IO-Link master, it's then converted or transmitted over whichever PLC protocol you're using to your PLC. So Profinet or Ethernet IP, yeah, and then you get the actual, your PLC reads that data from the microprocessor.
Okay, great. So the next two questions we have is regarding oil quality solutions. Are there general guidelines for oil cleanliness?
Okay, so for most motors, pumps, and valves, it's actually, there are some recommendations from the ISO 4406 standard, right? And this actually tells you the degree or the amount of particles that are tolerable and acceptable, as well as the size of it. So you can get this information from your specific manufacturer that will actually dictate this. Yes.
Once again, thank you, Rylands. Then can the LDH humidity sensor be used to detect moisture content in air?
Okay, so normally the LDH100 is marketed a lot for oil applications, all right? However, it can be used in air applications as well. You'll actually find that you've got to make sure that your pressure in your system is within the range of the sensor so it can handle it. And another important thing is that on the factory, this sensor is calibrated using air. So it most definitely can be used for air applications.
Thank you very much, Rylands. That's all the questions we have now in the area. If there's any comments or questions going forward, please post them on the Q&A section. We will create a Q&A PDF documentation which we'll upload on our website for you to look at. That's all from my side, Rylands. Thank you. You may continue with the presentation.
Cool. Thank you very much, Johan. And guys, I'm aware that we've covered various topics today on a very basic level. So I do encourage you to please get into contact with your nearest IFM sales office or your sales engineer to get more information on these products. And you are most welcome to follow us on our social media platforms like YouTube, Facebook, LinkedIn, and so on. And we are available, and this is where we post our latest product innovation and news. Also, guys, please be aware that our webinar schedule is available on our website, where you can find the webinars that are prepared in the near future to come, and also recordings of the webinars that have occurred already. So from my side, I also want to thank you for your attention and thank you for your time. And I wish you guys a good day further. So yes, thank you.